talk on behalf of three gentlemen, myself, Eddie Carmack, and Carlos Duarte. We have been involved in organizing a workshop on concepts and theories for a unifying pan-Arctic perspective and conceptualizing Arctic ecosystem processes in an area of climate change is the title of my presentation. And some of the outcome of that process, that workshop, I will share with you today. So we were invited by the Interagency Arctic Research Policy Committee. And so NSF, BOEM, ONR, and USARC agreed that there was a need for a high-level unifying paradigm for the understanding of Arctic ecosystems. And in response to that, we organized a workshop that addressed the conceptualization of Arctic ecosystem. It took place in November and was housed by the University of Maryland through Jackie Grepmeyer. So the goal was to develop a unifying pan-Arctic conceptual model of the Arctic Ocean. And 17 scientists from 60 nations convened in early November at the University of Maryland. So let me start with a citation of George Box that all models are wrong, but some are useful. And based on that citation, we can ask the question, for what are conceptual models useful? Now, a conceptual model you have to define, and there are many ways you can define them. But the definition which we launched, I will use, is that a conceptual model is a depiction of a process or a system, including its internal dynamics and its external drivers. And in the evolution of any given scientific investigation, a conceptual model is useful in four manners. It's useful by defining the scope of the problem and establishing testable hypotheses. It's useful by adapting a program design during the course of the investigation as new information is acquired. And in summarizing and communicating final results. Sorry, I didn't switch off my email, so we'll hear some sounds every now and then, but I can't leave my talk now. So working with conceptual models, or any type of scientific work, then scientists go through four stages: define, adapt, summarize, and communicate. So we plan to present a synthesis of conceptual models that have been applied in marine Arctic ecosystems. And what you hear from me now is just some elements of the ongoing process and work we are doing. And here right now, I can tell you that Eddie Carmack will come to Tromsø in early June and spend about a week here, dedicated to writing together with Bodil Blom on a paper where this conceptual model evaluation from the Arctic Ocean is the core of what we have planning. So in doing so, we will follow, we think, a scale hierarchical approach that recognizes regionality, seasonality, a pattern, and scale. And you will get some impressions on the three first of them in what I'm saying now. So, but to begin with, we have to have some philosophical words why conceptual models are essential for understanding of systems. And I think that's an important part, although some of my colleagues think that is more Paul Wasserman's excursion into philosophy and like that. But here we go. A conceptual models, they derive from a creative process that not only involves the virtue of scientific insight, but also suspicious activity such as intuition and imagination. So very often in science, we use reductionism, which is a very strong method of how to analyze a system, an organism. And reductionism helps us to exactly quantify an ecosystem composition. And we are trained in this and specialized in that. And I don't know if you look at the screen that you can figure out what the parts of a system, what system that is. It is a Christmas tree. But the exercise of putting down the system, here the Christmas tree, into its part gives us no clue how the system looked like or work. If we knew how the system was working, if we knew how the system would look like, then the quantification of the system would improve our insight on the content of that system. And here conceptual models come in. So a conceptual model like this graph here helps us to place the plots which we have found in our reductionistic analysis into a holistic context. But it's of course not realistic. Now, a second generation of the conceptual model or our model may be this one, a little bit more realistic. So the conceptual model needs to be revised in light of increasing knowledge. So at the end, the conceptual model derives strongly from experience, but also from the disregarded scientific qualification, and that is intuition. I would be surprised to have intuition and imagination as part of a curriculum at any college or university. And the intuition, which comes from not from the left brain of our brain, which we train so strongly at school and in our daily work, but it comes from the scientifically little trained right hemisphere. And there are some differences in the hemispheres, what they are doing. There's the left one, which is our daily bread. And then we have the brain function on the right side for the right-handed people, please, which has completely different qualities. And the real scientific progress means involving the entire brain. And what the conceptual model work is doing is it builds bridges from this intuitive, imaginative, how could things look like, how do they function, right brain thing, which are not derived from hypothesis testing, and then channel that insight into the left brain, and then we work it with this. And probably we can go left and right and left a couple of times in our pathway on progress. So this is a citation I like a lot. We have created a society that honors the servant, the rational mind, but has forgotten the gift. And now I don't think that Carlos Duarte or Eddie Carmack or anybody is especially gifted, but we have also some gift, and I would like to use that quality in our research. So then I switch to the Arctic and show you a graph that in all Arctic system, would we talk about the Arctic Ocean, then we talk about sea ice. Yesterday, today, and tomorrow. So the loss of ice brings about a cascade of changes in the ocean ecosystem. We know that because of increased warming, increased underwater irradiance, UV, increased stratification and ventilation. changes in reduced pH and increased CO2, etc., etc. And the interactions between these pressures increases the likelihood for observing complex responses and tipping points. And because of that, big changes in the Arctic, the need for conceptual models, good ideas how our mathematical models work and how we grasp the content on the system, that makes that we have to hurry up and do our best to come to adequate terms with the reality. So we will sort the conceptual models or the comparison between them and the further development into four qualities: in regionality, in seasonality, in pattern, and scale. And I will show you examples for the first three of them. Regionality. There is a strong regionality in the Arctic Ocean, as depicted in this graph. It shows the runoff area. The 10% of the freshwater of the world ocean goes into the world ocean, and how the entanglement of the Arctic Ocean between the Atlantic Ocean on one side and the Pacific Ocean on the other side. And those differences, and depending on where you are in the Arctic, that gives you a regional focus and a picture which reflects the regional aspect of the Arctic Ocean. And then the sum of the regionality is then the understanding of the entire Arctic Ocean. And this is a depiction done by Eddie Carmack and partly based on the work of Buddy Bloom, which, so to say, is some kind of a functional template which shows the Atlantic, the Pacific, the various land masses, their storm tracks, and the transport of fresh water from the tropical Atlantic towards the Northern Pacific, and the inflow of that fresh water into the Arctic, which shapes the entire scenario, which forms the ice. And then inside the ocean, we have the inflow, interior, and outflow shelves, the Lomonosov Ridge, and currents which enter and leave the Arctic Ocean. So that is, so to say, one of the more simple presentation of the Arctic Ocean. And we have to make a revision on the three different shelves, the inflow, interior, and outflow shelves. That is an old graph from 2006, but the functional modes and the biogeochemistry on the various shelves is completely different. And it has to be re-evaluated and reshaped. That is something we'll take care of. And in a horizontal scale, you see the difference between the various shelves. And the red one, what you see is the shelf break, which is an important domain for the Arctic Ocean. The regionality is also reflected in here in a graph which combines the dark, the sun, the light and dark period at various latitudes at the side here. See this on the left side. And then you have the time, January to February, on this side. And you see the disappearance of sea ice at various latitudes. You see the growth of ice algae blooms and the open water and the phytoplankton blooms. That is also a developed conceptual model, which we will look into with greater detail, in greater detail. So then I switched to seasonality. This is a graph which shows the seasonality of the marginal ice zone at about 78 degrees north in the Barents Sea. You see in white the snow and the sea ice, the melting of the sea ice, the rise of the sun from in March, April, until September, and how the breaking up ice and the ice algae gives rise to the phytoplankton bloom, and the sinking of particulate matter, fresh matter in green, and then the more recycled matter in red. And the ecosystem and the pelagic will turn from autotrophic phytoplankton dominated to red, let's say heterotrophic domination. And the three graphs, they show how that ecosystem happened or functioned before. That's a state which we already have left. In the middle is probably how it is functioning now. You see that the seasonality has increased by a month or 6 or 7 weeks. And in the future, while the ice gets thinner, snow cover, we don't know yet, you will figure out a new scenario where many of the players are still the same in different quantifications. The nutrients are still the same. The new production coming out of that production will always be the same, but the entire seasonality will stretch over 2 more months. And that means that the dominating organisms, which are opportunistic right now or have been before, taking that window of the first big bloom, that they have to be now they have to share with material over a much longer period of time, and that implies, we think, smaller phytoplankton species, smaller zooplankton species, less accumulation of fat, and all that ramification that has for higher trophic level of fish, seals, and other mammals. So that's the major change which has or it will take place in the future. We have also to revise the development in the high Arctic, the time to a minimum of 1.5 years, because in the high Arctic, the real high Arctic, meaning which has complete lack of sunlight, for that you have to go to 81 degrees north. There is an immense activity during the winter, which we didn't know only for 5-6 years ago. So a lot of ecological processes like reproduction, mating, and so on take place in winter. And the characteristic of the polar ocean of the biology is that they are not coping with 1 year alone. They need another season to get through that life cycle. So in autumn, they stretch, so to say, the surviving survivors. They stretch themselves into the dark winter period and come up on the other side. So we have to extend the life cycle of the time span which we're investigating and model for more than 1 year. At 70 degrees north, where I live now, or talk now, an annual cycle is adequate. And the more you go to the south from here, the annual cycle is, so to say, the big pacemaker. The more you go to the north, you have to expand that year for more than for the time period for more than 1 year. And that results in a major change in how we approach our ecosystems. And it demands that we have to work during winter with all the technical difficulties. So this depicts then maturing adults overwintering, egg larvae, copropodites, post-spawning adults, and so on and so on. And that picture which you see has to be fused with the picture which we developed before, and we have to make a new version taking care of that changed time aspect. Then I talk about patterns. The patterns to address the various patterns as a 2D in the Arctic Ocean, we wanted to develop further the different domains or contiguous domains, and a term developed by Eddie Carmack and me. And what you show here is the very little investigated riverine coastal domain. Most of our oceanographic vessels don't go into the shallow areas, but the freshwater runoff and the movement of anadromous fish takes place in this close to the shore, riverine coastal domain, which probably spreads around the entire Arctic as indicated in this graph, and where the river plumes are clearly visible when you fly over them by planes like this one. So this is a functional domain which is of a Pan-Arctic extent and which we know very little about. The next pattern which we have to talk about and look at is the shelf break and margin domain. This is indicated in red here. As you will see and have maybe taken note of already in real observations, very much of the productivity and dynamics take place at the shelf break. And the shelf break, in particular on the Eurasian side, are the region where the highest increase of primary production and new production will take place in the future. There will be much less activity along the shelf break, along the Beaufort Sea and the Canadian archipelago and Greenland. But on the Siberian and European sector side, a lot of changes taking place. And we see this quite right now already north of Svalbard and in the Kara Sea. So when the ice is leaving the shelf break and the wind is blowing from the east, then you get the shelf break jet, which results in an injection of nutrient-rich water from the deeper down. And that gives a shelf basing interaction in terms of upwelling, either horizontally on the shelf or right to the surface. The next domain is what we call the seasonal ice zone domain. Here you see in orange the seasonal ice zone as it had been. And this is the seasonal ice zone as it is right now. And then in white is the rest of what we could call overwintering or multi-year ice, which is steadily shrinking. Right now, the seasonal ice zone is 2/3 of the area of Europe, and the only vessels we have to investigate that seasonal ice zone. There is maybe a number of ice-going vessels, maybe 4 or 5 or 6, something like that, or more, to have some spotty investigation of that huge zone, which lies right in front of us. And what's taking place there now and in the future is difficult to grasp. And for that zone, we made an annual development seasonal ice zone. That is a new graph. On the bottom, you see a cross-section between the Kola Peninsula and the Beaufort Sea. That's a transect. You see the topography at the bottom. And then for every month, we have depicted a picture on how the ice is changing. The ice is the depth of the ice is exaggerated. And then in blue, you see the darkness, and in light, the light. And in green, you see the development of the seasonal ice zone, the bloom in the marginal ice zone. And you can see that you have a double bloom in April on the Atlantic side, much less so on the Pacific side or the American side. And then that phytoplankton development, then by July, which is big on the Canadian side, then it has already a subsurface phytoplankton bloom on the Atlantic side. And then in September, this signature. I have also made a graph like that, which shows how it might look like in 2050. So several of the conceptual models and examples which we show will be modified so that they indicate what we can expect in the near future. Below the surface, there is the Pacific Atlantic halocline domain, which is separated by the red line. And this animation, these are the waters, the streaming, the currents of the waters between 50 and 200 meters, and shows a clear separation between the Atlantic water and the Pacific water. And the productivity on the Atlantic side of those waters and the advection of zooplankton into the area is much bigger than on the Atlantic side, on the Pacific side. And you can see this in a picture from a publication of Bude Bloom, where you can see how much more biomass there is on the Atlantic side than it's on the Pacific side, although the Atlantic side is much heavily or much better sampled than the Pacific side. Finally, we come to what we call the advective domains. The Arctic Ocean is a circular ocean. It is driven partly by the advection of water through the Pacific advection or the Atlantic advection. And along with that advection, nutrients and specimens and organisms follow. And very often we have been talking and writing about advective domains, meaning we get longitudinal consecutive ecosystems which stretch themselves over 10 or 15 degrees of latitude and have a similar functional mode. That conceptual idea has been diversified, that we changed between the red Atlantic advection with the Atlantic forms and split up then the Arctic forms from the Barents Sea, which through the St. Anna Trough feed along the Siberian shelf. And then there is also the transpolar drift, which brings organisms and matter and dirt, in that case, from the Laptev Sea area across the Arctic Ocean into the East Greenland current. So these are the various 4 domains, which is a new development in light of the work which we started in November. The systemic challenge to use several concepts at the same time is of course enormous. And here I show you a graph which might confuse you. It confuses also us, so we have a hard time because this is a contemplate of conceptual models with the currents, animated currents. And these are the specific contiguous domains presented in one graph. And if you are here, you work here or there or another place, you will, in your samples, find the results of several contiguous domains, and you have to understand the content of what you find along several conceptual model suggestions. And that shows the complexity in the interpretation of our data, which we have to tackle. Now, towards the end of my talk, I show you just a little outlook. I show you some of our notebooks from our meeting in Maryland, in Solomons, and how we put those ideas together as a group of 17. Here is a depiction of the ecosystem from Central Arctic to Riverine domain, which will in one another form be modified and drawn in a much more nicer and attractive manner in our publication. We had also an artist with us who comes from KAUST, also Saudi Arabia. He joined us for a cruise in the Barents Sea last May to get tuned to the Arctic Ocean, polar bears, ice, and all that, so that he could see how scientists work. And he joined us for through the entire meeting and went to the various sub-meetings. And out of this sketch, he will develop a conceptual model, which will be available electronically. And it will have a central part, which shows the northern hemisphere, and then a cylinder on top, which gives you a 2D view of the Arctic Ocean. And there are different processes on left and right there, which I will then in the electronic version be clickable so that you can see what is meant with the various boxes. And it will probably look something like this, where the 1, 2, 3, 4, 5, and like that gives the specific conceptual submodels, which then illustrate what is not visible in this template. And the goal of that is that that model, at least the model which you see now, should be intuitively understandable for almost everybody who wants to understand what's going on in the Arctic. Should be attentive, attractive, and it is meant that that is what we mean by that a conceptual model is also a tool for outreach and to connect and to explain to more than the scientist what we are dealing with. Communication. So that is what I would like to tell you, and that's what I have. Thank you very much.